Okay, let's say that now we wanted to graph a quadratic function that wasn't in vertex form. Let's look at maybe if it was in factored form. Now, if I'm given this equation to graph this function, I should know that it's a quadratic because there's an x in the beginning of this first set of parentheses times another x at the beginning of the second set, and I know x times x is x squared. So that tells me that this is a quadratic function, although I may not see that power 2. Because I see 2 sets of parentheses, it tells me that my quadratic function is in factored form. We should know that factored form spits us out the x-intercepts. Without even thinking, I should look at it and know my x-intercepts. This has an x-intercept of positive 3 and negative 5, because if I compare it to that factored form that we discussed, remember it says x minus p times x minus q, where p and q are my x-intercepts. It doesn't say negative p and negative q, so we have to take the opposite of that term there. So I don't want to put my x-intercepts in the middle of my t-chart like I put my vertex. My vertex always needs to go into the middle of my t-chart. So what I do want to do is maybe let's start out putting them at the top and bottom. I should know, based off the fact of how a parabola, the shape is, I know that the x-intercepts are symmetric. So my vertex has to occur directly between my x-intercepts. So I need to locate the middle of 3 and negative 5. Now I can think of this by counting. If I know that negative 5 is here, and I know that 3 is here, then I could certainly count until I find the middle. There would be 8 units between negative 5 and 3, so I would need to go 4 away from each one. And negative 1 would mark the center. See, it's 4 units away from each of those x-intercepts. Or I could add those numbers together and find the average of them. 3 plus negative 5 would give me negative 8. Negative 8 divided by, 3 plus negative 5 would give me negative 2. Negative 2 divided by 2 would give me negative 1. And that's what I can put into the middle of my t-chart. Now, if 3 was an x-intercept, then I should know that its y-coordinate would automatically be 0. And if negative 5 was an x-intercept, I should know that its y-coordinate should automatically be 0. So I need to fill in some values in between. 3 is 4 away from my vertex, and negative 5 is 4 away from my vertex. So I just need some that are in between 4 units away. So let's just say we went 1 away. 1 to the left of negative 1 would be negative 2. And 1 to the right of negative 1 would be 0. Now, this time I don't know the y-coordinate of my vertex without plugging that value in. I know that it occurs at an x value of negative 1. I don't know its y-coordinate without plugging negative 1 in. So I've got to do some computation for those values. So let's start with our vertex. If I plugged in negative 1 for x, in my first set of parentheses, I'd get negative 1 minus 3, which gives me negative 4. And I'd get negative 1 plus 5, which gives me positive 4. So I've got a y-coordinate of negative 16 way down there. These two numbers, negative 2 and 0, remember, are 1 unit away from my vertex. So the symmetry will exist around those, just like the symmetry existed around my 2 x-intercepts. So let's just plug in one of those values. 0 seems a little simpler to plug in. I don't have to deal with a negative when I plug it in. So 0 minus 3 times 0 plus 5. That gives me negative 3 times 5, which is negative 15. Now, when I'm plotting this on my coordinate plane, I need to make sure that I'm probably going to take up about the whole page, really, going down with a vertex of negative 16 on my y-coordinate. So make sure you leave yourself enough room. We plot the points 3, 0, negative 2, negative 15. -1, -16, 0, -15, -5, 0. All right, now it should create us a U shape. So I see that I have 2 points that are symmetric there. Oh, there's my other 2 points that are symmetric, and there's my vertex. Very nice. So we can connect those points, and we see that that parabolic shape that created that parabolic shape resulting from my quadratic function. Very nice. Okay, let's do another one. On this one, let's fix our graph a little bit, our function. Let's put us in a multiplier. Let's say -3. Okay. All right. Let's see our x-intercepts. I see that this guy has got 2 x's. So x times x is going to result in a quadratic function because it would give me x squared. I know my quadratic function is in factored form, so it should spit out my x-intercepts very easily. This set of parentheses would give me an x-intercept of -1. This set of parentheses would give me an x-intercept of +1. So let's plug those in to my t-chart, leaving a little space in between because I know that my vertex should occur between those values. If I think about where those points are, -1 and 1, that tells me that my vertex occurs at an x coordinate of 0. And so these values are each just 1 away from my vertex. So let's go 2 away to the left and 2 away to the right. So fill in my t-chart and see the symmetry that exists. All right, let's plug in 0 for x. 0 plus 1 gives me 0. 0 minus 1 gives me -1. I'm sorry, let me say that again. 0 plus 1 gives me 1. 0 minus 1 gives me -1. 1 times -1 gives me -1. And then I've got this multiplier of 3 that's going to multiply every solution I get by -3. So it's going to stretch my graph some. So that would give me a value of -3 times -1, which is +3 for my vertex. So I got a vertex at 0, 3. If I plug in, let's plug in 1. We know that 1 and -1 are symmetric around my vertex of 0, 3. So if I find one of those y-coordinates, I'll automatically know the other one, and I prefer to deal with a +1. So if I plug in 1 for x, that gives me 1 plus 1 is 2. 1 minus 1 is 0. So I end up with a multiplier of -3 times the value of 2 times the value of 0, which gives me 0. That's easy enough. Let's plug in 2. So I'm going to plug in 2 here. We'll bring my multiplier of -3. 2 times 1 is 3. 2 minus 1 is 1. So -3 times 3 times 1 gives me a value of -9. All right, let's plot our points. Filled in our t-chart should create us a quadratic function, a parabolic shape. Okay, there's my vertex. There's my 2 symmetric points. And there's my other 2 symmetric points right down here. So I see my U shape. Now let's plot that function. There we go. Works nicely. Okay, let's do one more. Let's put us in a multiplier here too. Let's say a multiplier of 1/2. This might be a little messy here. Let's see what happens. Sorry, I'm getting this off my t-chart here. Okay, I see the 2 x's. That gives me a value of x squared because I'm multiplying them together. There's my times sign in the middle. I can tell that it's in it's in factored form, so that gives me my x-intercepts. So this first factor would give me an intercept of 2. This second factor would give me an intercept of 5. So let's put 2 and 5. Well, leave me some space in the middle, because no my vertex is going to occur in between there. But this one's a little trickier because I've got my 2. Think about where that value would occur. Here's 2. Here's 5. So I try to move the same amount, and it's going to occur at a fraction. It would have to occur between 1½ spaces between them. So, or I could do my average. 2 plus 5 is 7. 7 divided by 2 is 3½ So I'm going to have to deal with a fraction here. And we can still do our multiplication very easily. 3½ minus 2 would leave me 1½ I plug in 3½ to find my y-coordinate. 3½ minus 5 would leave me, let's make sure I'm doing that right. Let's get my calculator here. Just want to make sure. When I have to deal with fractions, I'm always careful. So let's say 3.5 minus 5. Yes, negative 1½ And I've got 1/2 times all that. Wow, that's a lot of fractions. So let's use our calculator to check our math. We would need to say 0.5 or 1/2 times 1.5 times negative 1.5. That gives me 1.125. Negative, because I didn't type in my negative, did I? There's 3 numbers. One of them's negative. Wow, that's messy. But that's okay. We're just going to create our graph from here. So we'll know that when we plot that point, we're going to go to 3½ So 1, 2, 3, and down 1, and just a little ways past that, not to the 1/2 mark. And when we're operating the coordinate plane and we want to plot a point that's not a perfect point or a perfect fraction, we just get in as close to that point as we could get. So we would go just a little ways past 1. All right, so 2 and 5 are 1½ values. To the left would give me 2, and to the right would give me 5. So what if we went 2½ values away, because I don't want to deal with plugging in another fraction. So, isn't that right? 3½ plus 1. Yeah, 5. So if I went 2½ values away, that would give me 6. Let's make sure I'm doing that math right. I want to go 3.5 plus 2.5, and that does give me 6. And then I want to go 3.5 minus 2.5, which is going to give me 1. So I'm making sure that I'm going the same amount away from my vertex. And I'm plugging in numbers that may not result, that I don't have to deal with fractions in my multiplication. And we're not saying that fractions won't result because I've got a multiplier of 1/2, but we're trying to avoid fractions in the multiplication of it. Trying to make it a little advantageous for us. Trying to delete some of this handwriting here. Okay, let's plug in 5. So 5 minus 2 gives me 3, and 5 minus 5 gives me 0. Oh, we knew that already. Those were our x-intercepts. So when I plug that in, we forgot to write that on there, didn't we? 1/2 times 3 times 0 is going to give me a value of 0. Which we knew anyway, because those were our x-intercepts. All right, now let's plug in 6. 6 minus 2 gives me 4. 6 minus 5 gives me 1. I want to take half that with my multiplier. So 1/2 times 4 is 2. 2 times 1 is 2. Oh, that worked out nicely. I didn't have another fraction to deal with. So there's just a fraction there. My vertex, which we're going to get in that vicinity. We should see the parabolic shape if we've done correctly. And it's really important for us to look for that all the time, but especially when we have fractions and decimals that are involved. I need to put a negative on that. Oh, I see it nicely. Here's my vertex. These 2 points are symmetric, and these 2 points are symmetric. So if we were to plot that function, it should pass right through those points. And it does. Let's talk for just a minute about what that multiplier is doing. This is a multiplier of positive 1/2. This was a multiplier of -3. Now, we've already discussed that the negative will make my graph point down. But let's talk about the 3 versus the 1/2. Look at the width of this graph right there between your vertex and your points that are one away from my vertex, one to the left and one to the right. See the width that exists between the branches of that parabola? And look at the width that exists between the branches of this parabola, in between its first points. What's occurring there is when that multiplier is a fraction that's less than 1, my graph will be a lot wider. We say that it is shrunk. My graph is shrinking the further away that multiplier gets from 1. Below 1, I'm sorry. When that multiplier is above 1, like a 3, remember the negative just makes it point down. So we're interpreting the width of that graph. We just think of it as a 3. That 3 is going to do what we call stretch our graph. It's going to make it appear skinnier. So it's important for me to think about that when I'm picturing the graph in my head before I create it.